As we get started, how many people here would consider themselves like data scientists? All right, how about application developers? Database architects or system architects kinds of people? All right, so a little bit of everyone. Thank you so much. I was kind of waiting for my water. My voice has been a little strange. I spent all week talking, which is bad for me and bad for the people who have to listen to me. So, my name is Ryan Betts. I'm going to give a presentation today about why to build a fast data pipeline, or how to think about data ingest in front of Hadoop or other OLAP systems. Like, this is the Hadoop track, so we'll focus a little bit on Hadoop, but the concepts are the same, regardless of whether you're applying an ingest problem to a Hadoop or to another system. And it's so loud. I feel like I'm maybe not talking at the right time, but we did start, right? So, all right. So, I'm happy with really interactive conversations. If there's questions, something doesn't make sense, you want to talk about the Red Sox instead of data ingestion, just raise your hand, let me know, okay? And I should also mention that this talk was put together mostly by John Hugg, one of my coworkers and colleagues at Volt, so a lot of credit goes to him for some of these thoughts. Figure out how to advance slides. Wow, it shouldn't be that hard. Wow. Thank goodness this isn't a talk about stability and applications, huh? Try number 2. No, I'm good. I think my keynote just crashed when we get started. So, a lot of big data applications look like this. People start to think about the volume of data first, and so the thing that they naturally focus on is collecting data into some kind of a repository. You end up having a number of different data sources. These could be log streams or sensor streams. They could be data from an IoT system, and you're collecting them with a number of different technologies and depositing the data that you receive, let's say in this case into HDFS, although it could be a columnar warehouse, it could be any number of other systems. And then from that columnar system or from that Hadoop system, you build a number of different jobs. These could be batch jobs, they could be analytics that are running on some kind of a continuous basis. But the important point is that they're largely read-oriented. Right? You've deposited a large corpus of information in some kind of a repository, and now you're reading that data for an analytical purpose. You kind of solved the ingest problem a little bit, and you certainly solved sort of a big data analytics problem, but what comes next? Well, the thing to notice is that these green sideways squares, these are largely movers, not shakers. So these are tools that are designed to transport data or to queue data to be available for another system. Oftentimes, when you want to begin to support an application against this ingest fee, you look for a way to write a real-time event-oriented application logic. You want to be able to take action on events as they're arriving. This is a relatively common need that's been emerging, and you're probably familiar with a number of tools that do things like this. So, for example, if you wanted to perform real-time counters, you might go from Kafka to something like Samza. Right? If you would like to apply some kind of logic or merging against data, you might run a storm pipeline after Kafka. Right? There are a number of different applications that are really interesting to be able to write against real-time data before that data hits a data warehouse. If you talk to a kind of an old-school database person, this is a really common concept. They say, of course, everything on the left, this ingestion engine and the things to the left, this is online transaction processing. This is what OLTP applications look like. Right? They're record-oriented, event-oriented, transactional, decision-making applications. The things to the right, the HDFS box, the consumers, the transformers, these are what OLAP systems look like, online analytics processing platforms. These are tools that are designed to efficiently store large volumes of data and that are designed not to transact on a record-wise basis against that data, but that make it very efficient to scan data largely for read-oriented applications. This is the same kind of split we're seeing. Here we're starting to see it with a number of different technologies. A lot of people have thought about Kafka, and a lot of people think about ingest. They kind of start with a tool like Kafka. So I'm going to use Kafka here as kind of a placeholder. There's a lot of different queuing systems. Certainly, in the people that I speak to, Kafka seems to be a very popular choice. So what is Kafka, what is it good at, and what's its role in this ingestion pipeline versus that little ingestion engine box? Why is a queue essentially not a sufficient solution for this problem? But the queue is wonderful at collecting data and then presenting that data as feeds to other consumers. And so Kafka is essentially a persistent queue implemented as a distributed partition log. If you follow Kafka, they've got some really wonderful papers on the log as a data structure and what that means and how you can use it. And it allows clients to read from a stream of data in a linear point. So every client basically keeps a reader bookmark for the data they've seen, and they can request a subsequent record, Right? So Kafka essentially is like a big capacitor for incoming data, and it allows you to connect multiple consumers to the single data source. So you can start to build pub-sub models and publisher-subscriber models out of this. But there are a number of other use cases that aren't simply about queuing and consuming that you want to be able to do in this fast data path or in this data ingestion path. Oftentimes you want to be able to filter, aggregate, or enrich the data before it arrives at your big data cluster. A common example of this is say that you're receiving sensor data from in-store inventory or from something that you expect to be moving in a large environment. And you want to record in your warehouse the start time and the end time of a device in a particular place. But the device is actually being read by a proximity sensor. So it's providing a reading every 100 milliseconds to you. You don't want to collect hundreds of milliseconds of readings or millions of readings that are just the device hasn't moved, the device hasn't moved, the device hasn't moved. What you really would like to do is create a session for a device for the location where it was positioned. You want to know the time that it entered that position, and you want to know the time that it left. Right? So how do you get that information? There's a couple of different approaches that you can take. You could write all of the device data to Hadoop in this case, and then you could write ETL jobs that would go back over that data, read it all, and rewrite the final session records back. Right? Or, in this case, since the data is arriving in real time, you can perform that operation by using a tool in front of the warehouse. And in many cases, it's advantageous to perform operations like that in front of the warehouse because it gives you both operational insight into the data that's arriving. It allows you to identify missing records. It allows you to, for example, in a smart grid infrastructure, to understand if there's correlated failures to the different concentrators that are recording data. So, for example, in a smart metering, an electric or water metering system, you might have tens of millions of meters. These are big nationwide projects that are all being read every 15 minutes. Those readings are first read from the meter and passed to a concentrator. There are about 100 meters associated to every concentrator. You would like to be able to know in relatively real time if missed meter readings are correlated by concentrator. Right? You would like to understand if the operational error is just that a meter is dead or that if none of the meters associated to a particular concentrator could be read. Having an ingestion engine in front of this kind of path allows you to do these operational workflows essentially in real time. That allows you to effectively, as the slide says, lower the latency to understanding about what's going on. You also find a number of situations where you have high concurrency readers who want access to this kind of operational data. In a call center environment, you may have many dashboards that are showing the utilization of the people in your call center, along with perhaps real-time billing and real-time kind of length of call. Right? If you're in a large call center, you take very careful notice of how your staff is interacting, how long they're spending on the phone, how many times they're dialing out in an outbound call center. These are essentially key business, key performance indicators. And there are a number of different activities within the business that want real-time visibility to that. So you need some way to read in a high concurrency way all of this real-time data. It's another function that's popularly done in this ingestion engine point. What are some of the different constituent parts of an ingestion problem? I like to look at this problem in two different ways. I like to look at it both from how is data flowing through this particular component of the infrastructure, and then I like to think about what is the data necessary to support the real-time application. Because effectively what's happening here is that you're taking the applications in your enterprise and you're making some of them very real-time event-oriented. Once you can do, like the Spark demonstration that was here just earlier, showed some really wonderful real-time analytics that you can do on Spark. Once you have the capability of performing those analytics in real time, you want to be able to structure applications that can make decisions, that can execute transactions, that can have immediate side effects based upon real-time state. Right? This is a relatively common concept. It's been referred to, for example, as HTAP, if you were an analyst fan and you had to watch the new mumbo jumbo that they produce. But effectively what it means is that for you to derive value from real-time analytics, you need to be able to couple that real-time analytics to an operational procedure. Right? Say, for example, how often as a human do you actually receive new information? A person can watch a dashboard, and maybe that dashboard updates once a second, and someone can take a unique action maybe once every couple of minutes while they're watching. However, in many circumstances, you would like to be able to take personalized actions on a per-event basis in milliseconds, not in minutes. And you would like to be able to take unique actions for every event hundreds of thousands or millions of times a second in a smart grid infrastructure or in a sensor-based infrastructure or even in just a mobile network that's doing contextual marketing based upon what the user just did, right? Or in a free-to-play game environment that's tuning its environment based upon your kind of assignment of player type and what you just did in the game a couple of seconds ago. All of these situations are producing an operational requirement. I'd like to be able to take an activity or have an impact, and they're all requiring a real-time analytics component as an input to that operational event. Right, so once real-time becomes faster than a person, then you need to automate that. And automating that means integrating it into an operational application, and that application is going to require some kind of data management support to manage both the historical wisdom, the segmentation, the report, the predictive analysis that you've derived from the OLAP side with the operational transactional component from the real-time event-oriented side. And so that's one way to look at this from the point of view of data flow. You have incoming inputs and potentially per input response data. You have some kind of processing that occurs. You have a pipeline of the data that's being kind of injected from the real-time system into Hadoop for long-term collection. And then oftentimes you have direct query of the streaming analytics or the streaming state that's being maintained here. So you have at least these three interesting data flows. An incoming event-oriented stream, an outgoing sort of ETL processed stream, and then a query stream. And the real-time ingestion engine can kind of be broken down into two components, the compute component or the processing component, and then the state that's required to perform the processing. So you can also think about these applications from what state is, oh, there's a question. That's awesome.
The form of that state, is that state global or is like for the distributed system that is locally existing?
That's a great question. So the question is the state global or is it distributed? Usually we find that most of these systems are distributed systems for scale. So that state ends up being distributed. But it's a great segue to kind of discussing what the different pieces of state are. So oftentimes if you have an operational application that wants to use some analytic result, you have some kind of a report or a model that you've derived from your OLAP system. The metaphor I like for this is that your OLAP system or your Hadoop system is sort of a source of wisdom, right? It's all of your memories. And you data mine that, you perform data science against it, and you try to find discoveries or potential optimizations. And you structure those as reports or models or search indexes, right? You structure the data that represents the wisdom that you've learned from that OLAP system. So that's one piece of data that's here. So I kind of alluded to one use case. This is one of my favorite use cases. I like to talk about it. But a VoltDB customer does online game optimization. It turns out that if you're making a free-to-play game, the key is to keep the player engaged so that as the player plays, they continue to see more game content, more advertising opportunity, and more chances to get you to purchase something for 99 cents, right? So the key of the platform is to maintain player engagement. Once you begin to move past kind of naive methods of doing that, you effectively need to combine two things. You need to combine your best guess about what that player likes with the information about what the player just did. You're going to take those two pieces of information and combine them into some kind of a tuning parameter that you think will best optimize the platform for their play experience so that they play longer, see more advertisements, and buy more good games for 99 cents, right? So in that case, the pieces of state to solve that problem are one, the session state, what's the real-time player state? What did the player just do over the last couple of seconds? It's second, it's the data that you derived from your OLAP system, that model or that segmentation report that told you how you should optimize the game for that player. In many cases, you'll see when people solve this kind of a problem with something like Storm or Cassandra, they're explicitly separating the processing from the state management. You'll have a Kafka queue that's feeding a Storm pipeline. Storm will be doing processing, but it'll be reaching out very frequently to some kind of a lookup engine to retrieve data. And as it computes its analytics, it's writing those analytics back to what? To another storage engine so that they can be queried. And so that's a great illustration of the three main components here, right? The incoming event stream, Kafka, the resulting analytics need to be placed somewhere for query,